Let us talk about this question. We are given a matrix which is row-wise sorted and column-wise sorted. We are also given a value x. We need to find out if this value is present in this matrix or not. If it is present, we need to print its position. And here in this example, it's not present. So we need to print not found. In both the examples, you can notice that matrix has every row sorted in increasing order 10, 20, 30, 40, 15, 25, 35, 45, 27, 29, 37, 48. This is also sorted in increasing order. Every column is also sorted in increasing order 10, 15, 27, 32, 20, 25, 29, 33 and so on. This matrix also has every row sorted in increasing order, every column sorted in increasing order. Now please pause this video and try to write down a function that takes a matrix as input, a value x as input, and this function should print the position of x if it is present, otherwise it should print not found. Let us first talk about the naive solution. Time complexity of this naive solution is big O of R into C. I have written here pseudo code for the naive solution. This code is close to C++ and Java codes. The idea is really simple. We traverse the matrix like normal traversal row-wise. As soon as we find the element x, we print the location and we return. For example, if we're searching for 29, we'll begin from here, we'll come here, come here, come here, and then we'll traverse this row. Then we'll come to this element. At this position, we find 29. So we'll print this position. This position is 2, 1. I and j we will print and we'll come out of the function. That's what we do in this implementation. We run a normal matrix traversal code, basically 2 nested loops, and then inside these loops we compare every element ij with x, we find it, we print its location. Now if the element is not present at all, suppose you are searching for something like 51, then you will traverse the whole matrix, and once you come out of the loop, you would not have returned at any point in the middle, so you will come here and you will come here only when you did not return in this particular if. So you will print not found. So this is big O of R into C solution. This is a very naive solution. It does not use the fact that your matrix is row-wise sorted and column-wise sorted. Now please pause this video and try to write down a function that uses this fact and finds the element in big O of R plus C time. It's a linear time. Let's now talk about the efficient solution. This efficient solution is slightly tricky. The idea is to begin from top right corner. Traverse the matrix. While traversing, compare x with the current element. If x is same as the current element, then we are done. We print the position and we return. If x is smaller than the current element, then we go to the left side. We basically ignore the whole column. And if x is greater, then we go to the downside. We basically ignore the whole row. Let's see how does this work with this example. Say we are searching for 29. We'll begin from the top right corner, which is here. 29 is smaller. If x is smaller, we go to the left side. So we'll come to 30. Right? Now 30 is again greater. X is again smaller than 30. So we'll again go to the left side. Now x is greater this time. When x is greater, we go down. So we'll come here. Now x is greater. 25 is smaller than 29. 29 is greater. X is 29. So we come here. At this point, x is same as the current element. So we found 29 and we print it and we return. Let us see how does this work. We began from this element. Since 29 was smaller, we move to the left side. And are we not missing anything? Since this is greater, it means all these elements are also going to be greater because it's a column-wise sorted matrix, right? So we can safely skip all these 3 elements. When we moved to the left side, we actually skipped these elements, right? Now when we come here, we again see this element is greater than 29. So we skip these 3 elements also. We go to the left side. And since 30 is greater than 29, these 3 elements are anyways going to be greater than 29. They cannot match with 29. So it is safe to move to the left side when the current element is greater. Now when we came here, we saw that 20 is less than 29. In this case, what we did, we skipped this row. So we skipped all the previous elements in this row, which means we skipped this 10 here. Since this 20 itself is smaller, all the elements on left of it are going to be smaller. So skipping this row was fine. We did not miss any valid element. So when I say skipping this row, I mean skipping the elements on left side of this row. These elements have anyways been skipped. So we came to 25 and we again saw that 29 is greater. So we skipped this row also. Right? We skipped this row. These columns have anyways been skipped. So we skipped this 15 also and we came here and we found 29. We printed it and that's how the solution works. Let us now do one more example. Say we are searching 39. We'll again begin from here. 39 is smaller than this. So it's going to be smaller than all these elements also. So we'll go to the left side. Now 30 is smaller than 39. 39 is actually greater. So we'll go down. Now we come to 35 and we again notice that 39 is greater than 35. So we again go down. See, when we are going down, we are actually skipping these elements. When we went down here, we skipped these two elements. When we went down here, we skipped these two elements. Right? Now 37 again is smaller than 39. So we skip these two elements also and we go down. And at this point 39 matches with 39. So we return this position and we print this position and we return. Many of us have this curiosity, why from top right, why not from any of the other three corners? Let's try analyzing the other three corners. If I begin from this corner, what will happen? If I'm searching for an element which is greater than this, then I can clearly tell this element is not present. But if the element is smaller, then this element can be present anywhere. So I cannot decide whether I can skip this column or this row. That's why we do not begin from here. And the same reason applies to this. If I'm searching for an element which is more than 10, then I can surely tell that this element is not present. But if the element is greater than 10, then I cannot decide whether to go here or to go here. Talking about the fourth corner, we can actually use this corner also. So in our solution, we can either use the top right or we can use the bottom left. We can write similar rules. If I'm searching for an element, if I find it here, I return. If I don't find it here, and if the element that we are searching is greater, then I go to the right side. And the element that I am searching is smaller, then I go to the up. So instead of writing left and down, I can go right and up. So we can begin our solution or write our solution from any of these two corners. Now you understand the solution. Please pause this video and try to write down complete code for the solution. Let's see the implementation of efficient approach. Here I have again written pseudocode and we begin from the top right corner, I equal to 0 and j equal to c minus 1, row 0 and column last. We run a loop and inside this loop we have three things. We either find x at matrix ij, in that case we print and we return. We stop our function, we immediately return. And the other case is when matrix ij is greater than x, like 29 and 40, it's greater than x, right? This is greater than x. So we go to the left side. For that we do j minus minus. And the third case is when matrix ij is smaller than x. Like if we are searching for 50, then we'll go down, right? So in that case we do I plus plus. That's a simple idea. And while doing this j minus minus or I plus plus, if we cross the boundary, if I becomes equal to r or j becomes less than 0, then we stop this and we say we did not find. That's the simple idea. Let's understand this with 29 example. We begin from here. 29 is smaller, so we fall into this case. We do j minus minus, we come here, right? So I've written the j value here. These are the initial values. When I come to this point, I see that it's again greater than x, so we come here. Now this is smaller than x, so we do I plus plus. And when we come here, we find the element, right? So initially j is 3, then j becomes 2, then j becomes 1 at this point. Now I becomes 1, right, at this point, and at this point I becomes 2. And when I becomes 2, in the next In the fifth iteration, you are here, you find matrix Ij equal to X, you print this and you come out of the function. Let's now do an example where element to be searched is not present. Say we are searching for 24 in this matrix. So what are we going to do? We are again going to begin from here. 24 is smaller, we are going to come here. 24 is smaller, we are going to come here. 24 is greater, we are going to come here. 24 is smaller, we are going to come here. 24 is greater, we are going to come here. Now 24 is smaller, we are going to go to the left side. When we go to the left side, j becomes minus 1 because j was 0. When j becomes minus 1, you come out of the loop, right? You run the loop while j is greater than 0 and I is smaller than r. So when we come out of the loop, we print not found. So that's how this solution handles the elements also which are not present. Let's now talk about time complexity of it. In every iteration, we are either changing the column or we are changing a row. So in the worst case, we might change all the columns or we might change all the rows or we might do a mix of these two. So the overall time complexity is big O of r plus c. We can slightly optimize this implementation. If the element to be searched is smaller than the top left, then we can immediately print not found and return. And if the element is to be searched is greater than bottom right, then we can print element not found and return immediately. Because the top left is always going to be the smallest element in such a matrix and the bottom right element is always going to be the greatest element in such a matrix. So we have talked about both naive and efficient solutions and we also talked about a slight optimization over this efficient solution.